Hello and welcome to this episode of Physical Attraction, where we will be interviewing Brynley Pearlstone, who is a gravitational wave astronomer and host of the SciCurious podcast, which is a podcast dedicated to LGBT people in STEM. We'll talk about both his scientific career and his outreach work. I hope you enjoy the show. Okay, first of all, hi Brynley, thanks very much for coming on the show.
Thank you for having me.
Let's start by discussing a little bit about you. So when did you first get interested in physics in general and decide that you want to study? Was there a light bulb moment, or was it just something that you were always interested in?
I have a distinct memory of being in my secondary school back in Somerset, and there was this teacher. He was a physics teacher, and he was talking about how all these hippies in the 60s wanted to name different flavors of quarks after different flavors of ice cream. And the idea that you could have so much fun with something that's so typically dry was really enticing to me. And the idea that I could sort of make sense of these complex systems and that it would make sense of the universe was also quite enticing to me as well. So ever since that, I've had this sort of interest in physics that I couldn't undo. And then walking around in the world, whenever I saw some kind of a system, whether it was the axles in a car or the mechanics in a game where it modeled something as an ideal gas to spread pressure out, then I'd sort of try and work out the physics of it, break it down and see if I could work out, sort of deconstruct it into its component parts. And that was sort of the lightning moment where I said to myself, this is how I see the world, why not go and learn about it? But there was a brief wobble in the middle where I fell madly, deeply in love with Darren Brown. And so after college, I put on my UCAS form to go away and study psychology. And if that had come to fruition, we'd be having a very different conversation right now.
I think we should say just briefly, because I know that most people who listen to this are actually in the US or Australia from the stats. Darren Brown. Do you want to tell us about who Darren Brown is?
Darren Brown is sort of P.T. Barnum of our time.
He's a bit like a magician, isn't he? But a sort of psychological magician.
Stage hypnotist stroke showman. So he has all these big TV stunts where he tricks people, I suppose, hypnotizes people into doing things they never normally would. They range from drinking a glass of vinegar to staging a bank heist. And they're all very complex. And he does it mostly through showmanship and sheer charisma. And I sort of wanted to have that power over people. It sounds weird when I say it like that.
Yeah, I mean, I can sort of see what you mean. It's one of those things about the level of people's suggestibility, I suppose, and most people think they aren't very suggestible. But actually, one thing I did notice about Darren Brown is quite often when you listen to the spiel that he gives people, he tells people, actually, a lot of people think that if you're able to be hypnotized, you're unintelligent. But in reality, it's the intelligent people who can be hypnotized more and so on. And so it's sort of planting these suggestions that being, malleable or suggestible to his will is more of a marker of intelligence than anything else. And I think that's quite clever the way he does it. But I must say, aside from that, I haven't seen much of his stuff. Okay. So, I mean, it's interesting that you mentioned your teacher as well being a source of inspiration, and also the naming of quarks, because we have the truth and beauty quarks of what they were originally going to be called, the T and B quarks, and then they ended up with the name of top and bottom. And I often wonder whether, like, the bottom quark is a bit annoyed that they missed out on being called beauty and ended up being called bottom instead. Yeah, fair enough. It's an interesting thing about the teacher though, because I remember there was a debate the other day online where people were talking about when it comes to teaching physics in the classroom. Typically, the first thing that people get taught in school is Newton's laws, Newtonian mechanics, F equals ma, and all these problems with blocks on inclined planes and sleds and so on. There was a debate raging about whether Newtonian mechanics was the best thing to teach people. Because on the one hand, it's mathematically very tractable, right? You can come up with lots of quite simple problems with Newton's second law. But on the other hand, it's not that inspiring to think about, okay, this is a force that's pushing on a block here, this is a force that's pushing on a block this way. Obviously, if you're trying to teach something about black holes or astronomy or cosmology or anything like that, you're going to struggle to get it to a mathematical level where kids of 10 or 11 could reasonably solve problems on it. But at the same time, it's much more interesting to deal with this kind of problem. So where would you stand on that? Do you think that the role of physics teaching in school should be to give people mathematical problems that they can solve predominantly, or is there a place for this kind of trying to inspire people by showing them what you can infer with physics and mathematics?
I think both are true. I think you do need to have the basis of mathematics if you're going to go into further physics, right? You and I have both been through education in physics to a higher degree level, and you need that strong mathematical basis. But that's not to say it can't also be inspiring. And I also want to question the sort of assertion that you start learning physics with Newton, because you sort of don't. In preschool, you're all about dropping parachutes with eggs and splitting the sun through a prism and rolling carts into each other and seeing what they do. And that's all finding an intuition for how physics works in a really fun and engaging way. And there's no reason you don't have to stick with that further on. Even with these sort of Newtonian problems, it doesn't need to be as dry as here's a 30-degree plane and a block. You could jazz it up. For example, Newton's third law of body in motion, or continuing motion, is perfectly applicable to space battles. A spaceship is traveling this far in this direction. How long does it take? You need to apply the brakes for 20 seconds. How strong do you apply them? I think it's very, very easy to jazz up these kinds of problems and make them more interesting. But that said, just because we traditionally start with Newton doesn't mean we need to. I do think you need to find maths in there somewhere, and you need to start somewhere where it is intelligible easily and intuitable easily. The great thing about Newton is that you can easily make an experiment out of it. You can push a block and see that if it's static, you need to push it harder, and if it's up a plane, you need to push it even harder. So it's very easily intuitable. And there are other parts of physics that are like that as well, but they aren't springing to mind.
Yeah, but there are some parts that I guess you can't really do unless you have access to a colossal telescope or a big fusion experimental reactor or something like that, which you can't really bring into the classroom so easily. So, I mean, later on, after your sort of high school days, you moved into astronomy and specifically gravitational wave astronomy. So, would
Right.
you like to talk about kind of deciding on that as a topic to choose?
It was I sort of fell into it. I went away to university. I didn't get the grades to study psychology as I would have wished, and so I snuck into a physics course and didn't do terribly well at first at university. I almost failed my first year there, but from second, third, and fourth year in undergraduate in Wales, getting my undergraduate masters, I really sprung back and ended up with a first-class master's degree in general physics. I only took one, maybe two astronomy courses. There's a little wrinkle here in the history of South Wales, which is that Swansea University, where I studied, and Cardiff University used to be one. They used to be the University of South Wales. And when that body split, Cardiff took most of the astronomers, and Swansea took most of the particle physicists. And so at Swansea, there was a large a large proportion of experimental and theoretical particle physicists. So I got a lot of particle physics in my undergraduate, but not so much astronomy. Following my masters, I moved home back in with my mum and took up work for a year, working in an ultrasonics plant. But living with my mum in rural Somerset, not being able to drive, my partner being sorry, can we edit that? My my boyfriend being 200 miles away in Swansea, I didn't really fancy sticking around, and so I looked for a whole bunch of PhD applications. I knew that I wanted to satiate this curiosity about the world. I didn't know what I wanted to do. I had hedged towards particle physics because it's what I knew. But a friend of mine, who I'd met from Cardiff University on an away day somewhere, was at Glasgow in this gravitational wave group, and she happened to post on Facebook, "Anybody looking to do a PhD?" And I said yes. And then the next week I flew up to Glasgow and had an interview with my supervisor, and told him I'd quite like this place, but I've got a couple of other offers for different universities. Can you give me a firm but informal offer? And he said, certainly. And the rest is sort of history. I definitely just sort of fell into it. But the thing that really won me over was the ambition of gravitational wave detection. I was looking to do PhDs starting 2014. Advanced LIGO, the detector that we're going to talk about shortly, I'm sure, only started operating in 2015. And so it was a pre-detection era. So it was all sort of up in the air. The theory was there and it was solid. I learned a little bit about it in undergraduate. My master's thesis was about the theory of general relativity, particularly closed causal loops. I like to say that I've got a master's degree in time travel. And the idea of being able to apply that in a very real way to find some long thought result in this absurd, absolutely absurd setting felt like a good challenge.
Yeah, I can definitely agree with that, and certainly a very exciting time to get into gravitational waves when you did. Can we talk about this a little bit then? Because so let's start with the basics to remind people. We did cover these briefly on the show a few years ago when the LIGO collaboration won the Nobel Prize. But can we start with your description of what is a gravitational wave?
Right, so a gravitational wave is technically it's a plane wave solution to the Einstein equations. More informally, it's a wobble in space and in time. So, general relativity describes space-time as a sort of material through which the universe exists. And so, when you've got something that is very heavy, it tends to sort of tug on this material and creates a dip in it. The visualization that I like to use for this is you've got a trampoline and you put a bowling ball on it. There's a dip in the middle of the trampoline where the bowling ball is, and that means that other things can fall into that dip where the bowling ball is. In this example, a bowling ball is some massive object like the sun, and something else that falls into it is a planet or a moon. And even holding this example, if you whiz the ball around, it will circle this dip. But the gravitational waves sort of come up when you have two bowling balls that are circling around each other. So two massive objects in space that are both in this material of space-time, and they're orbiting around each other, or even just accelerating. They have this really interesting radiation. It's not quite the same as just ripples in the sheet. It's not quite the same as just the variations in gravity detected from these moving objects. It is a very specific kind of quadrupolar radiation that is sort of transmitted as a wave through the material of space and time. And that wave has the effect, it's a transverse wave, I should say, so it acts orthogonally to its direction of propagation. And it has the effect of stretching the very definition of meter in one direction and squishing it in the other. And so if you were to hold a ruler up to a gravitational wave as it passed through you, at one extreme of the wave, the ruler would be longer. The meter in that ruler would be longer. And then at its minima, it would be shorter. And similarly, it will be fatter and thinner as well. And to go with that, time also stretches and squeezes. So if you were to run a stopwatch through a gravitational wave with an impartial observer, at the wave's maximum, it would be the second that you measure would be longer, and at its minimum, it would be shorter.
So these are the sort of vaguely familiar, I guess, ideas from general relativity of length contraction and time dilation that are being propagated out through space by these gravitational waves.
That's
So
right.
you've talked about having these two very, very large objects circling each other. Can you give us some ideas about the sort of objects that would emit gravitational waves? And not just that, but also because the amplitude of these waves, if I'm right, is falling off like r squared as you go further away, as is the case with, say, a light signal and so on, purely because you can imagine them spreading out over the surface area of a sphere as you move away from them. And so to actually have something that is observable millions of light years away, how sort of large I mean, technically, I suppose we're producing gravitational waves even as we walk around.
Right.
But to have something large enough that's going to produce these gravitational waves that can be detected over these astronomical lengths, what kind of astronomical events are we talking about?
So, to the first question, what produces gravitational waves? You are correct. We all produce gravitational waves. Any mass that accelerates will produce any kind of gravitational wave. But the hitch here is that space-time is really stiff it's really, really hard to pump enough energy into space-time to actually get it to move any, which is why gravity is such a weak force. It's why a fridge magnet can stick to a fridge rather than sticking to the whole Earth that we're standing on. Space-time is sufficiently stiff that in order to create gravitational waves, which are these sort of higher order effects and of the plane wave solution, is that you need something really, really heavy. So the first detection of gravitational waves, for example, was also the first direct detection of black holes. It was a pair of black holes, both around 30 times as heavy as our sun, and they were orbiting around each other about 1.4 billion with a B light years away from us. It's really hard to constrain that length distance number just because of the way that we do parameter estimation. But just to think about it, 30 suns worth of mass in each black hole orbiting around each other and colliding over the course of 0.1 seconds. That one event alone, for its duration, radiated more energy than all the stars in the observable universe just through gravitational wave energy. And at the detector, it produced a absolute change in the length of a meter of 1/10,000th the width of a proton.
By the time you get billions and upon billions of
That's
light years
correct.
away.
Yeah.
But it does make you wonder. I mean, it's like all of these questions that I think people often have about things like black holes and neutron stars would be another good example. Of just the question of what it would look like to actually observe these things from close up. And I suppose from a kind of practical point of view, the answer is you'd just be obliterated and destroyed by being an observer standing that close. But we can sort of see the ripples of these events from some distance. But
So I actually read a study about this. If you were able to stand up close to a black hole and survive its effect, as it were, and feel a gravitational wave of a pair of colliding black holes, it would be about the same as standing next to a speaker at the club. You'd feel it pulsing through you. But compared to being ripped apart from head to toe that you'd normally feel from a black hole, this extra effect is minuscule, if anything. It's really hard to pump energy into gravitational waves. So I'm a neutron star guy. There are a whole bunch of sources for gravitational waves. Parallax black holes is only one. We can classify the universe into we can identify a class of objects in the universe as compact objects, and this would include things like black holes and neutron stars, and maybe white dwarfs if you're feeling lucky. And as long as they're very, very heavy, they can produce relativistic effects. And so you could also imagine having gravitational waves from a pair of neutron stars or a neutron star and a black hole colliding together. And in fact, I think all three now have been observed. But you can also observe gravitational waves from single objects. For example, you would take a star that goes supernova. So long as it's spherically asymmetric, you've got some overall acceleration. And so you can imagine gravitational waves from that event. Or a single isolated neutron star, such as the Crab pulsar, rotating, as they tend to do. Rotation, as we know, is a form of acceleration. And it can radiate gravitational waves over a very, very long period that are so weak. If we were to imagine a mountain on a neutron star, and I use the word mountain here very loosely, we're talking millimeters to centimeters high, then that creates a mass asymmetry while the neutron star rotates, and that creates a wobble in its moment, and that can generate, theoretically, very weak, very long-lasting gravitational waves. My research specifically was in this kind. We call them continuous waves. But I was looking for even more. I was trying to find a way to detect even more niche than that. We know that some pulsars, some neutron stars, do not always act as we think they do. We expect neutron stars to be pretty regular. They spin at a very fixed frequency. They slowly lose energy to their surroundings, and that's it. They're like a spinning top that slows down gradually over millions of years. But sometimes, particularly in young neutron stars, they can have what's called a glitch, which is where we're not really sure what goes on. It might perhaps be a superfluidic pinning in the superfluid core of the neutron star reacting with its crust, or just a crust quake. but it's a transfer of energy from the core to the crust, and the neutron star appears to speed up in a moment, and then over the course of a little while, it decelerates more quickly, and it returns to its normal progression. And so I was looking for gravitational waves from these kinds of events, called transient continuous waves, quite confusingly, because it's hard to be both transient and continuous.
Transient and continuous at the same time, yeah.
Mm-hmm. But we expected them to have the morphology of a continuous wave, which is just pretty much a sine wave, but have this sort of transient nature on the scale of weeks, days to months.
So we should say here that given that a neutron star, which is this sort of intermediate end phase for a big star, which if it was heavier would collapse into a black hole, and if it was lighter would not collapse into a neutron star and instead would be a white dwarf. These things end up being about 10 kilometers in radius. So
Right.
if you're talking about a star quake on a neutron star, you're talking about movements of some incredibly dense star material, but perhaps only by a few meters.
Not even centimeters to millimeters.
Centimeters to millimeters, and this is going to produce signals that potentially, with the technology that we have on Earth at the moment, could be detected.
So you wouldn't necessarily detect the starquake itself. You detect the recovery of its spin pattern from the starquake or from the glitch.
I see. So it's the change in rotation rate of the star as a result of the starquake.
Exactly. You can think of the deceleration rate of a neutron star's rotation to be analogous to the amount of energy it's radiating away. And so if that changes, if that increases, then you know that it's radiating away more energy. But if nothing else about the star changes, it's still in the same nebula, you don't see any changes in its pulse width or luminosity, then they have to be radiating somewhere. And so gravitational waves is a pretty good guess.
When it comes to neutron stars, do we actually have many other ways of observing them? Because it's as you say, so you talk about gravitational waves as a solution to Einstein's field equations. We know that also black holes are a solution to these field equations, where for quite a long time, although it was theorized that these things could exist, it actually took a while for them to be indirectly detected. And one of the really exciting things about gravitational waves is that there are these objects that obviously aren't luminous and can't necessarily be detected in the same way, but they have to be sort of inferred by their influence on luminous objects. We now actually have a direct way of observing these based on the gravitational waves that they're putting out. So, I mean, aside from the gravitational waves, how else have we understood things about neutron stars and black holes in the past?
Let me tell you a story about my favorite scientist, a woman named Jocelyn Bell Burnell. She was a scientist in Cambridge where she was doing her PhD. She's a radio astronomer, and she was setting up a whole new array of antennae for the brand new telescope they were making back in the 60s. I think it was 67 she started. And she was doing the thing that observational astronomers do, which is setting it up for a short period and then troubleshooting everything for a long period. This is a process that I refer to as detector characterization. What does your detector look like when it's operating normally and doesn't have a signal? And she'd looked at all the possible sources that could be in her spectrum and eliminated them. But there was one noise that she couldn't get away, a regular pulse of radio waves that were coming in a few times a second. And they could not for the life of them work out what it was. And for a few years, she and her supervisor were spitballing ideas, and they came across a paper about the possible theorized existence of a neutron star, a star made entirely of neutron matter. A neutron star does have an electromagnetic proponent. We know that a neutron star has a magnetic field, much like the Earth's magnetic field. We know that a neutron star is in the universe, so it's not on an island. It's definitely connected to everything else. And this magnetic field is really, really strong, like crazy strong, much, much stronger than the Earth. I don't have a number.
I think we're talking like 10 to the 9 Tesla compared to the strongest magnetic fields that we would generate on Earth, which might be of order 1 or 2 Tesla.
At tops, yeah.
Maybe 10, 50 Tesla tops. So
10 to
obviously
9 Tesla is
your fridge magnet and your fridge magnet and the Earth's magnetic field are far, 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 far less powerful than these neutron stars can produce, which is beyond anything we've ever made or studied on Earth.
But the Earth's magnetic field is strong enough to produce the aurora borealis, When we have
Exactly.
particles coming in from space, interacting with the field, they give off some radiation when they interact with our field, and they give off these aurora, these glows that we can see in the north and south hemisphere. The same happens at a neutron star, but because their fields are wild, instead of just having a faint, nice, pretty glow, it's kind of like a lighthouse. So they've got this big beam, this huge, bright beam of electromagnetic radiation coming out from their poles. And I've already told you that neutron stars rotate. And so these beams tend to sweep through the sky across the path of their rotation. And if we're lucky, and we have been a number of times, they sweep over Earth and we can detect them. And that's how we've been detecting neutron stars up until now, is just through the sweeping of their beams. And that is, I should say, the signal that Jocelyn Bell Burnell saw on her spectrum. It was a regular pulsing from a pulsar, which is where they get their name from, the radiation coming out from a neutron star. At first, it was termed LGM1 for Little Green Men 1, because they didn't quite know what it was, but has since had a proper neutron star designation.
And then, of course, famously, Jocelyn Bell Burnell was unjustly passed over for the Nobel Prize for discovering this, although she now sort of says that maybe that was one of the best things that ever happened to her because she's won every other award.
She has.
So I think one of the exciting prospects surrounding gravitational waves is this idea that we have astronomy with additional messengers. So, previously, as you say, we had to look for the electromagnetic components of what things are doing. We had to look for these radio signals and things that come from these various different objects in space. For example, now we're starting to see the first few events where a supernova, for example, or a black hole merge or a neutron star collision will occur, and we'll get both this electromagnetic signal and a gravitational wave signal at the same time. And when you think about how much of what we know about cosmology and astronomy comes from just having the signals that come from light alone, what else are we going to be able to discover? What other things might we be looking into and finding out about if we have an additional stream of information to interpret when one of these major...
So on the 17th of August 2017, one such event did happen. A pair of neutron stars orbited around each other and collided, and it was picked up in LIGO's Advanced LIGO's second observation run. It's an event we call GW 170817. GW for gravitational wave, and then the number is the date, 170817. And that was the first detection of a pair of neutron stars orbiting each other by gravitational waves. The automatic pipeline of LIGO was able to send out alerts quickly enough to astronomers. It was also picked up by the Fermi satellite as a GRB, gamma ray burst. And over the next few weeks, a whole bunch of LIGO's collaborators who work in electromagnetic observatories trained their telescopes on the spot that we were able to pinpoint using clever triangulation techniques, and we're able to observe it electromagnetically as well as gravitationally. So we have radio, optical, infrared, all kinds of, and X-ray, all kinds of spectra of this one event called a kilonova. Kilonova have been hypothesized for a long time as a pair of neutron stars colliding. As they do that, as they draw close, the tidal forces from each star rips the other apart. They spew nuclear matter into the universe, which decays, giving off some lovely radiation, a nice little fireworks show. Then they finally collide and create a quasi-stable, super heavy neutron star, quickly decaying into probably a black hole. And through all that, they've got all the pulses from the poles of the neutron stars. They've got a whole bunch of energy released electromagnetically as the two magnetic fields interact and combine. There's a whole bunch going on there. It's all been modeled, and it was all also verified after GW 170817. They are able to show that through this one event, one Earth mass worth of gold was produced alone. One Earth's mass worth of platinum was produced. It was hypothesized for a long time this is probably where the universe gets so many of its heavy metals, and we're able to say yes, heavy metals are produced in abundance in these events. We were able to measure the Hubble constant by a completely separate metric. in the past we've used standard candles, supernovae, to measure the distance to distant galaxies. But now we've got this other method, a standard siren. We can think of these events as sirens. They sound like a chirp, like oop. And because neutron stars sort of inhabit the same mass range, these are standardized. And so we can get its distance completely independently of electromagnetic readings, which means we can measure the velocity of that galaxy, and now we know its distance independently. It's another measure of the Hubble constant. We were able to study what happens when you do have two neutron stars colliding. We didn't constrain it particularly well because it's very hard to do, but we were able to say we can look at this now. A whole bunch can come of this, and I also want to point towards gravitational waves isn't the first time we've had multi-messenger astronomy. Kamiokande and other neutrino experiments have been engaging in multi-messenger astronomy for a little while, but now we've got a new messenger to add to the bow, which is fantastic.
So we should describe this just very briefly. The Kamiokande experiment, I think, is a neutrino detection experiment. And basically what they have for this is a huge vat of usually water or something along these lines. Neutrinos are these ghostly particles that are leptons that are produced in lots of astronomical events, and many of them come from the sun as well. And typically a neutrino, there are many, many billions of neutrinos passing through you all the time. So their interactions with ordinary matter is quite rare. And that's why you need such a vast tank as the one they have in Kamiokande to have a statistical probability of detecting one of these really, really rare cases where a neutrino interacts with another particle. The one advantage you have is because they don't interact so often, they're actually less likely to be deflected by the magnetic fields and the electromagnetic fields in our galaxy and in our solar system and between galaxies and so on. So I guess, yeah, like you say, there have been some events where we've observed neutrino signals from them as well as visual ones. And I really like the analogy of this way of detecting the Hubble constant as a standard siren rather than a standard candle, because it's as if we have another sense to look at the universe. We're listening as well as watching now.
Absolutely. Well, it's funny you should say that, because the time stream, the data stream that we get out of LIGO is from each detector, we get a one-dimensional wave, and the gravitational waves that they're sensitive to are 20 to about 10,000 hertz, which is about the same sensitivity as our ears. And so you can actually go online and hear these gravitational waves as they sound in the detector. We don't see them. We don't have, one detector doesn't give you a good sense of directionality, but you get to hear them. Combined, different detectors can give you an idea of where things are. These are completely analogous to our ears to the universe.
One of the things that you did as part of your PhD research was working with the LIGO collaboration. What was that like?
It's strange. I suppose it's more the normal in these times when we're all stuck at home and on countless video calls. But I was in a group of maybe 50, which is quite large for an academic group at Glasgow University. With those, I directly interacted in my workday with 2, 3, maybe 4 tops who were doing similar things to what I was doing. The rest of my collaborators were dispersed around the world. And so every week I'd have several video conferences, conference calls, and getting to know people just by their emails, which is not uncommon these days. One thing I did get to do was go out to Washington State to the detector site at Hanford and get a bit hands-on with it there. That was fantastic, but also kind of strange being in such a foreign place for 4 months. Gave me an insight to who I was talking to through the conference calls. And so that really sort of shed light that I was working with this vibrant and diverse and brilliant and hardworking collaboration, not just people who existed for an hour of my week and then went away and did some things and then came back.
And I think it's very interesting. I mean, this art of how to collaborate better. One of the points that came up when we discussed this as the Nobel Prize is that science, and particularly physics, is advancing much more now by these big collaborations by a great many people, all of whom contribute a little bit, or some of whom contribute a lot, and so forth. But it's certainly a lot more like that now than our traditional vision of, and our outmoded vision of science as a few lone individuals who come up with breakthroughs that change the face of everything. And in light of that, there's been a lot of discussion. We've now had 2 major prizes that have been won by effectively 3 people, but on behalf of a collaboration. So we're talking about LIGO and Atlas, and I'm sure there are others if we went through the prizes. So, I mean, the prizes themselves should be reconstructed. That's one of the topics of this, but also a more broad reason, a more broad thing to talk about is why the prizes should be reconstructed, which is that science has really changed, and now it is about this mass collaboration. It is about this summing together of many, many, many individual efforts in a far greater way than it was even 30, 40 years ago.
Mm-hmm.
So what do you make of that, and your sort of opinions on how, well, I suppose, how we can collaborate better, and also how we should think of science in this era?
So this is something that I call or I've heard called the great person model of science. And this comes back to the first question. We learn Newtonian physics. We don't learn classical physics, we learn Newtonian because they're named after
Mm.
Newton, the person who did all the work of finding them out. Except we find that he didn't necessarily do all the work. He did a lot of very important work, but he wasn't alone. He had people working in his laboratory with him. There was other work going on at the same time that he would talk to others and collaborate with, just in not such a formal and organized setting, because that kind of bureaucracy wasn't the norm back then. And so there's this famous story of Newton and Leibniz. Probably without both of them, they might not have gotten calculus done. I think this idea of great person science is definitely outmoded and never really was true. Even down to Einstein's stroke of genius with all the relativities. He wasn't working alone. There were already ideas of curved spaces and
You have Minkowski and Lorentz and people like this who
exactly.
were in a similar era coming up with similar ideas.
Exactly. They were working on ideas of metrics and the ideas of combining space and time into a thing. He just happened to put all the pieces together in the right way. Without all of his peers, we wouldn't have Einstein. And so, great person science hasn't ever really worked and shouldn't be how we think about science. So now we come on to the collaborations. The collaborations have always been a thing. Now we're seeing more and more large collaborations. And that's because all the easy stuff is done, right? We've got classical physics, we've got thermodynamics, and now we need our LIGOs and our CERNs, and that is not a small person work. That is thousands of people working in concert, doing a little task each to add to the sum of a whole. And even if their contribution is some offhand comment that sparked an idea, or making this small part of computer code to plug into the larger whole to go into the analysis, every bit of it is as crucial as the next. What we saw in the Nobel Prize was that the leads of the investigation were awarded the prize. Deservingly so, they've been sticking with it for the longest time. But they weren't the only people who were there at the start. And there are other people who've had as big or bigger contributions since. And so I think you're right in that we need to shake up how we think about awards. There are other awards, I should say, that do recognise the work of collaborations. For example, the Special Breakthrough Prize was awarded to the entire collaboration, with the credit being split 1/3 to 3 people and 2/3 to the rest of the collaboration. And I think that's, maybe I'm biased, but I think that's possibly a better way to be thinking about this, as there might be chief actors here who instigate the whole thing or have contributed a lot, but without the whole collaboration, you don't have the result. And in terms of collaborating better, it's really important to have this sort of recognition of the structure formalized, and to have every part of the machine recognized for what it does and how it does it. And that's very hard to do in an everyday setting when your Joe walking down the street only wants to see the headline and then maybe read the article and that's it. Not everyone's going to do a deep dive into which parts of the machine were built where and who was most instrumental to this part. But if they want that, it should be there. I think it is for the most part now. And that does a lot for collaborators, making them feel that their contributions are as valued as they are.
It's interesting here because so often when I'm doing this podcast, I find that there are easier ways to tell a story than others. So quite often, if I want to tell the story of, for example, relativity and how that developed, it makes sense to focus on an individual character and an individual personal story. And I
Right.
just think both we and the way that media interacts with science and institutions is it's much more about personal stories than overall trends and forces and organizations and things like this, which are a lot more difficult for people to get their heads around and focus on. But I think it's a skill that we really need to develop to have a better understanding of not just what's happening in science, but in all sorts of different fields around the world and around politics and culture and economics and so on.
I think the difficulty here is that personal stories are very compelling, and the obvious personal
Mm-hmm.
story to tell is the one that got the glory, because they are the victor in the end. They get the glory, they get the result they need. It's a good story, but it's not the only story to tell. You could still tell the story of relativity, for example, through one of Einstein's mentors, or by a loose collaborator watching from the wings as Einstein pulls these pieces together, but definitely narrate it from somebody else, for example. But when you've got a collaboration like CERN or LIGO, you've got 1,000 of these stories to tell, and it's very difficult to tell the story of a bureaucracy. Not very compelling. I sat down and did paperwork. I made a conference call. Not good listening. But if you were to hone in on a person with a particularly interesting story that isn't perhaps often the most recognized, then I think you've got a winning combination. And this is why I love the story of Jocelyn Bell so much, because she didn't get the big prize, but she was a collaborator. And since she's gone to find the recognition that she deserves.
So we've had the LIGO and the Virgo collaborations, which have been very successful, and they've spotted these events that we've talked about: mergers of black holes, mergers of neutron stars, mergers of black holes and neutron stars. What's next in the field of gravitational wave astronomy? Are we going to build more detectors? Are there different events that we're looking for now? Or is it a case of waiting for some interesting events to show up and sort of continuing to reap the benefits of the collaborations that exist at the moment?
Well, we've got LIGO and we've got Virgo, and as of the end of last year as well, we've got a collaboration called CAGRA, which is a gravitational wave detector situated in Kamioka, which is where Kamiokande is. So that
Mm-hmm.
creates a cosmological theme park, as it were. You can go and get your gravitational wave candy floss and your neutrino hot dog and go and sit in a mine and have fun for the whole physics family. But on top of that, we are always looking to the future. As I'm sure you know, big science doesn't happen overnight. And so there are already plans down the road from 2030, 2040, and onwards. For example, advanced LIGO isn't done being upgraded. Sure, we've got the big money shot, but it doesn't mean that our work is done. There's still gravitational waves coming at us from all angles, from all corners of the universe, that have yet to be discovered. For example, gravitational waves from isolated rotating neutron stars, which I spoke about earlier. We've yet to find them, but we know they're out there. At least we're pretty sure. And gravitational waves from supernovae. We've yet to find them. Gravitational waves, something we call the stochastic gravitational wave background, which is sort of this rumble in the background of a whole bunch of these compact binaries coming together that are too faint to distinguish individually. They create a background curve from which we could learn loads of cosmology. So there's a whole bunch still to learn, and to that end, there are new detectors popping up all over the world. Kamioka has one, Kagra, which has only just come online. They're building a LIGO in India, which is colloquially termed Indigo, or LEGO India, which is less fun for me to say. Um, China has been looking at building a detector for some time now, and there are plans for a triangular configuration detector in Central Europe, probably Germany, called the Einstein Telescope, to replace the Geo 600 prototype that has been in Hanover for a long time doing its job. On top of that, we plan to leave this planet behind entirely. You might remember a few years ago, there was a mission from ESA called LISA Pathfinder. That was a trial mission for a project called ELISA, the Long Baseline Interferometric Space Antenna. which is a triangular array of lasers, which are a gravitational wave detector orbiting the sun in, I think, behind the Earth and along the Earth's orbit, tumbling in a constellation, trying to pick up gravitational waves on a more galaxy, supermassive black hole scale over the course of a 5-year mission. And so there's plenty still to do with gravitational waves. We are by no means done with what we're doing. It's just that we've got the big money shot and we've proved the proof of concept. Now we just got to go do the work.
So the field is sort of still, although it's now been demonstrated to work, it's kind of still in its infancy potentially in terms of what we might find in the future, particularly with some of these new projects. It's very interesting.
Absolutely.
And the ELISA project, I guess that would work in a vaguely similar way to LIGO, in the same sense that at its core you have a sort of interferometer where you're measuring the differences in lengths between arrays of different lasers. Is that right?
That's right. The sort of key here is that your lasers are now something like 10 to the 5 kilometers apart from each other. And so you've got this huge baseline where LIGO is only 4 kilometers. I say only, but 4 kilometers for a laser travel is pretty far. Now you've got 10 to the 5 kilometers in a triangular configuration tumbling around in space behind Earth. And the key challenge here is trying to keep the lasers and the mirrors and the photodiodes all in alignment with these millimeter shifts and keeping them still, as still as you possibly can, relative to each other. LISA Pathfinder was able to show that not only were they able to do that well enough, they were able to do that well enough in LISA Pathfinder that it should be good enough for the main ELISA mission.
And in some ways, this is the really incredible thing about gravitational wave detection, is that the signal that you're looking for compared to the background noise of things that could be happening is so tiny. And so the sort of the noise reduction that one has to do to be able to reliably detect these changes in this distance is a real precision task and undertaking.
And that comes in the form of both hardware and software. So I want to break that down for you a little bit if I can, because I find this so fascinating to talk about and so fascinating to think about.
Yeah, please do.
I mentioned earlier that the first detected event had an absolute distance change between the laser lengths of 10 to the minus 19 meters, the 1/10,000th the width of a diameter of a proton. 10 to the minus 19 meters is wild. There is no way that mirror was stock still so that you could see 10 to the minus 19 meters difference in it. And the way that we get that number is we shoot the laser down the 4-kilometer tube into a mirror. It reflects back and goes back and forth through a Fabry-Perot cavity, sort of amplifying this minuscule length change hundreds of times before it recombines and interferes with the other stream of the laser. These length scales, the temperature of the mirror at each end is
because the mirrors will be vibrating due to the temperature that they have.
Exactly. It's a measure of the kinetic energy of each molecule of the mirror. And so in order to account for that, we have a larger laser spot so we can average over this random temperature. We know that the Earth is going to move. A fun story about this is that my mentor, when I was out on site, once caught the cleaning staff racing up and down the arms just by looking at the seismometers placed around the site. We use those seismometers so that we can exclude events that are contiguous with a earthquake or some weird seismic activity. But to isolate from that, we also have them suspended from a pendulum, on a pendulum, on a pendulum, on a pendulum. So 4 layers of pendulum, each one producing F squared, frequency squared level of isolation from the ground. So really, we're trying our best to make it as stock still as we can, even before we get to the computing. And the computing is wild as well. A lot of the best structures use a Bayesian template matching algorithm in order to find the signal in all the noise. But first of all, you have to convolve out all the noise, which means you have to know what the noise looks like, which is a massive undertaking. Every single part of this project is completely insane. I love it so much.
Yeah, it's just incredible when you think about talk about finding a needle in a haystack. You're finding a billionth length of a needle in a haystack that stretches from I don't know, Land's End to John O'Groats, or from Boston to New York, or something along these lines. Sorry, my geography is terrible, guys. I don't know how long that distance actually is. So it's just incredible that in some ways we can even say anything about these events, but it seems like the amount of ingenuity that science and humanity in general has to infer as much as we can about the universe from relatively tiny signals is unabated. And I think it's one of the best things about astronomy, in my view, is just to think about how we're able to infer so much about how the universe works from such relatively small evidence. There's the starlight that falls on Earth and things of this sort. So it's a really really fascinating area of research. So outside of your direct scientific research, you also host a podcast, SciCurious, which highlights LGBT people in STEM. Can you tell us how you decided that you wanted to start the show, how you found the podcasting experience, and some of the people that you've been able to interview so far?
So I started the show at the end of my PhD. I was coming to the end, and I knew I wanted something to do with my time. I knew I didn't want it to be too strenuous, because I wasn't sure what was next, and I wanted to have enough wiggle room in my schedule. And podcast got me through my PhD. I'm sure all listeners are probably fervent podcast listeners. You don't just put on one podcast. Once you find one, you find a couple more. It spiraled to the point where maybe 6 hours out of the 8-hour workday, I'd have a podcast on. If I'm just coding, I can have a podcast on. It's a different part of my brain. I can code just fine listening to Night Vale or to 20,000 Hertz. There's a whole bunch out there. I just really enjoyed listening to podcasts. And I felt like I had this knowledge of the medium and intimacy with it, and wanted to give back to it. I also knew that as an out scientist, I didn't always feel seen. I didn't necessarily feel that I was appreciated within the scientific scope for as a whole person. I always felt like that was sort of put to the side. And so I wanted to show that LGBT people can be scientists too, and that we can be whole people in and out of the lab. So combining these ideas was natural. The format of the show is a 60-minute episode, each one with a different researcher. Excuse me, hang on. Right. The format of the show is a 60-minute show, each one with a different researcher who happens to be queer. And the thesis is, I want to highlight people. The idea isn't necessarily talking about the science all the time, or necessarily glorifying this part or tokenizing them. I just want to say, you're here, you exist, you're valid, and you're doing what you're doing. And explore them a little bit and get to know them a little bit. And hopefully the listeners can get to know them too. And through doing that, I've spoken to a whole host of really interesting people. About this time last year, I was in London, and I spoke to James Claverley from the National Physical Laboratory. He is the diversity chair for the Institute of Physics, and they were just on the cusp last year of releasing their workplace climate for LGBT people in physical sciences report. And so I got a couple of ahead of the curve sort of takeaways from that during that interview. That was a really fascinating talk with him, just trying to work out what his human elements are, because obviously he's a human. Let's just get to know him a little bit. And it was really, really fun chatting with him. More recently, I've spoken to Emily Harford, who's a nuclear engineer, and she happens to be the sister of Tim Harford. But she is so outspoken. I saw her speaking at a LGBT STEM conference in January of this year, and she spent her 15-minute talk standing up for the E in STEM and talking about how nuclear fusion, which is her work, is so viable. If only we put a fraction of the amount of money that we put into the Qatar 2020 World Cup into nuclear fusion. I think everyone that I speak to has their own viewpoint and this interesting outlook on life. And it's just so refreshing to hear so many different people's takes on their field, on their research, on the state of the world today. I'm sure you have a similar process through this podcast.
I mean, I have found doing this show, originally, I never really intended to interview people. I found the interviews the best part for me, personally. I love
Mm.
researching and I love writing scripted episodes, which is what most of the episodes of this show are. And that's always fascinating. But just the ability to, yeah, as you say, talk to people, get to know them as people behind the science, behind the scientific papers. And I think just getting to speak to people about things that they are passionate about and hearing what they have to say and seeing them as rounded individuals, it does make you feel a lot less alone as a scientist. Because I think there are, I mean, one of the major issues, particularly with graduate research, is a sense of, you're okay, you may be part of a collaboration scientifically, but the research you're doing is very much your own thing. And I don't know, it can be quite isolating. And I think that one way of getting around that is realizing that everyone who is a scientist isn't just a list of citations or a list of published papers or anything like that. They all have their own lives, their own stories, their own motivations, and their own perspectives, both on the field that they're in and, as you say, other issues, the state of the world.
Yeah, I wanted to say something to that, and that is this feeling of isolation that we have as, or that I had as a graduate researcher. Um, I think a lot of it comes down to this feeling in science, certainly in the physical sciences, that you as a researcher need to be objective and not invested too much in your research. And that means you're not invested too much in your research group, and that means you don't necessarily always feel comfortable being an entire person in the workplace. I think that as a concept sort of needs to be reassessed. Physical sciences and the laws of our universe are going to be the same whether or not we wear that rainbow pair of socks into the workplace, or whether or not we come in and be our full kooky selves. I think if we all feel a bit more comfortable being ourselves in our workplace environment, maybe that sense of isolation will change a little bit.
Because as you say, physics especially, it suffers from a really strong stereotype of what a physicist is. The stereotypical physicist that people will imagine, I'm sure people are imagining at home now, is quite a strong archetype, even compared to other sciences, let alone other fields.
If you're listening to this, can you pause the podcast, draw a physicist, and tweet it to me? That's at B Pearlstone with the hashtag MyScientist, because I want to see what you're thinking about.
Okay, guys, everyone, get your pens ready. Get your artistic software ready. Get going. Was that draw a scientist?
Hashtag MyScientist.
Hashtag my scientist. Okay, hashtag my scientist. Um, yeah, so as we say, there's these stereotypes. Maybe our listeners will have a different stereotype, or maybe they won't have one. But I remember when I first arrived as an undergraduate, there was a committee of students who welcome you in. They asked me what I studied. I said physics, and the first response was, "Oh wow, but you look normal," as if I should have had antennae or something.
Right.
I mean, that's a funny example, really. But I have absolutely no doubt from my own experiences that there are still serious incidents of queerphobia, homophobia, misogyny occurring regularly in physics. And I feel like it's probably more of a problem in physics than even in other sciences, let alone in other fields. And ultimately, as well as very clearly being unfair and immoral, this kind of thing is detrimental to science, because if we're only an open community to a certain kind of person, we lose out on what everyone else has to bring. And we've talked about how important these huge collaborations are. There are things that we are missing out on because of the attitudes that prevail in science, unfortunately, at the moment, I think. So, I mean, what do you think we should do and can do as a community to communicate this message that physics is for everyone?
So I want to pick up on a couple of points you raised there. And one of them is that the queer, gay, the queer, homo, bi, transphobia associated with the physical sciences. And to me, I see these going hand in hand with institutionalized misogyny, institutionalized racism. They sort of breed together these intolerances, and they tend to be, unsurprisingly, in fields which are male dominated. And I think I don't have the answer for that. The answer to that is make the conscious effort to hire diversely and promote diversity at every opportunity. And that doesn't just mean hire only the gays and the women and people of ethnic minorities. It also means hire people who are in the majority, because diversity isn't just everybody else, it's everybody. But highlight diversely.
And also diversity of backgrounds, diversity of ideas, diversity
Yeah,
of ways of thinking, and diversity of
absolutely.
the means in which people are qualified for a particular job, right?
you don't have to look very far to find situations where a lack of diversity has really impacted negatively on a product or on a project. We take the Apple Watch, the first generation Apple Watch. They had a whole heap of health tracking. You could track your heart rate, your sleep cycles, your blood pressure, all kinds of things. One thing that it missed was a period tracker. And of course, that's roughly half the world's population. If there'd only been a couple more women on the engineering team, perhaps they might not have missed that. And so this is where diversity comes in to all things, where it can not just human sciences or biological sciences, but in all things, diversity of ideas, diversity of backgrounds, diversity of people will really go to make whatever you do work better. What was your question? I forgot.
That was basically it. It's just essentially what should we do to communicate the message that physics is for everyone. And I think a huge part of it is the work that you're doing with SciCurious, which is to give people these examples that they can look at and say, okay, here's a counterpoint to the stereotype of a physicist that I might have in my head, which is showing me that, you know, that there are people like me who can contribute and, you know, enjoy themselves in this community. And yeah, I think that's one of the most important things that is avenues for this representation to get out there.
Well, I think one other way that we show people that science is for everyone is to show them that it already is for everyone. You're just not being shown it. I'm sure you know as well as I do plenty of people in physics from all kinds of backgrounds, all kinds of upbringings, all kinds of people doing physics. But you look around on the headlines and you always see the same few stale, male, and pale people being highlighted. And that's fine to have a couple of old white cis straight guys, but it doesn't represent the whole of physics. And it already is so diverse. We just don't see it. That's what I'm really trying to do with SciCurious, is just to say, look, we're already here. Let's just speak up a little bit.
Mm-hmm. I think it's extremely important because it's not just a question of becoming more effective as a scientific community, I guess, by inviting more people in, but also just because it's the right thing to do. You know, you don't have to go too far into the utilitarian aspect of things to say, obviously, we want to be the kind of community where more people feel like they can be physicists and can get involved and can bring what they have to the table. I mean, there's no downside to that. So I think it's really important. So we've got SciCurious, your podcast. What else should people do if they want to keep up with your work?
Well, they can find me on Twitter, either at bpearlstone for my personal account, or at SciCurious_pod, which is SciCurious' account. I tweet from both of them quite regularly. They can find me on Instagram at SciCurious Podcast, or on Facebook. You can find SciCurious at SciCurious Pod. Or go visit my website, which is scicurious.co.uk. You can see a theme emerging.
Yes, SciCurious is the place to go. Okay, Brynley, thank you very much for coming on the show and talking about your research and your engagement.
Thank you so much for having me.
Thank you for listening to this interview with Brynley Pearlstone. You can find his work at SciCurious on Twitter and online. You can find his podcast, the SciCurious Podcast, which features interviews with a different scientist, every episode on their life and works. If you would like to find out more about our show, you can go to physicspodcast.com, where the contact form is there. You can send us any questions, comments, concerns you might have about the show. You'll find the Patreon there, where you can subscribe for small fees per bonus episode, and you will get access to half a dozen bonus episodes that are already up there and more on the way. You can donate to us on PayPal at paypal.me/physicspod. The link is also on the website there if you want to give us a tip for producing these episodes. But of course, the best thing you can do for the show is always to tell as many people who might be interested to listen to it to listen. Until next time then, please take care.
Thank you.